Yeah, hopefully I don't get heckled too much. You never know. One can always hope. Let me again put on a better pointer for those in the Zoom. Uh, right. So was everybody there on Tuesday? So I don't have to reintroduce two things. Yeah. Cool. So yeah, a bit of a shift of gears. Today is really more for people unfamiliar with EEG. So I'm expecting Pete to answer all the questions that you might have. Yeah. Is that fair? Sure. So first off, it's the 100-year anniversary of EEG this year. So Hans Berger first described human scalp EEG back in 19. Whoops, there's an obvious typo. 1924. He's a very futuristic scientist. But there are a few objectives I want to try and get through today. One is to really talk about the role of the reference electrode in EEG and ERP analyses. Talk about the added value of doing high-density EEG. How to measure properties of the electric field at the scalp, meaning its strength and its topography, and how that leads then to a pipeline that I would argue allows for more replicable and comparable analyses, especially in efforts to make science more open and solid. So as probably everybody knows in this room, the methods are very young. EEG is the oldest by far. MEG came about in the late 60s, PET in the mid 70s, TMS and non-invasive brain stimulation mid 80s, fMRI 1990, and FNIRS in 93. And we can consider all the methods on multiple axes, whether it be spatial resolution, temporal resolution, but also in terms of causal inference that we can derive from whatever measures we're taking. And we can put various sizes of spheroids on these axes, and they're moving because you and others are further developing these techniques. Sorry, I realized that some of my slides are in French. So yeah, teach in multiple languages, but I think the translation is pretty straightforward, if not. fMRI doesn't, as you know, allow for causal inference about what's going on. It's more about correlational inference. On the other hand, brain stimulation gives more causal inference because you're directly impacting, of course, the neural tissue. EEG, like MR and fMRI, doesn't allow for a lot of causal inference. But what EEG really does have is temporal resolution that fMRI today doesn't yet have. Again, these are very dynamic bubbles. I think it's also important to remind people, perhaps, that if this is too, it was very hard for me to know what level to put this at. So if it's too simple, just say, move on. If it's not simple enough, also tell me so that I target things better. So EEG is not measuring action potentials. Hopefully everybody knows that. We're measuring postsynaptic potentials onto apical dendrites, right? So you can model the electric fields around this neuron in terms of its extracellular current. Sinks, well, depending on whether it's excitatory or inhibitory, but let's suppose it's excitatory. So extracellular current sink would be surrounding the apical dendrites, right? And current source near the zone, right? And therefore you can model the neuron as a current dipole, like a battery. Okay. But again, we're not measuring individual neurons either. We're measuring populations that are simultaneously active in similar ways. So volume conducts in circles. And the analogy that we've used in the past is comparing somebody doing an interview one-on-one with an athlete as being like measuring intracellularly, measuring local field potentials would be like being inside the press box inside a stadium. And of course, being outside the stadium, hearing the roaring of the fans inside would be like what we're measuring with EEG. It's not a perfect analogy, but you get it. So some other aspects that I think are important to think about in terms of EEG are cost-benefit analysis. So one aspect, of course, is the cost. An EEG system, a high-density EEG system, under 28 channels, will cost you about 60,000 euros. You can negotiate, and most, if not all, of the analytic software that you'll use is either free or open source. So that makes EEG very, very, very affordable compared to other techniques, whether it be MEG, or even MR, you're talking about orders of magnitude cheaper. Right? The lifetime of an EEG system, if you treat it well, is at least 10 years. I think if it's not lasting 10 years, you're probably doing something wrong to your hardware. I even have amplifiers that are probably 30 years old now that work just fine. It's lightweight, wireless. I think we were talking about this earlier. Nano EEG you can put in a backpack. You can even put it on a smartphone, and that'll work. It won't necessarily always be high density. It's relatively easy to use. You can train up people quite easily. Students as well can be trained really in a short period of time, and you don't have the same safety concerns. They're different safety concerns as with MR. So it's quite accessible now. And again, the temporal resolution is obviously quite nice. And you can nowadays record from 512 channels, even more if you wanted to. I don't know why you would, but if you are. And it's accessible from neonates to the elderly, to people with claustrophobia, to implants. And you can combine it as well with other modalities, which you guys obviously look at well. You can also combine it with PET, which I'm surprised that there isn't more of in terms of neurovascular coupling. Maybe because PET's kind of gone out of fashion, but it's kind of a pity because you don't have to deal with all of the headaches of doing simultaneous EEG MR. You can also combine it with pharmacology, physiology. You can also do this in real world environments. And you can get away from overt behavior if you design the right types of paradigms. We'll come to that later. So there'll be a series of these throughout the talk, some of which are targeted to Peter. MEG has a higher spatial resolution than EEG. True or false? True. You didn't even hesitate. Yes, true. 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 This is false. And who would say I love that? Well done, Peter. You played into it very well. It's not actually true. It's true if you're comparing apples and oranges. If you're comparing different numbers of sensors with MEG with different numbers of sensors with EEG, of course, more sensors usually should give you better spatial resolution. But in fact, if you compare apples to apples, so the MGH team, who are biased, if anything, towards MEG, have done this. And Mel, are there any Finns in the room? No. Okay. So Mel did a nice job talking about this, and we did some work on this as well, where if you compare the same numbers of sensors, the spatial resolution actually isn't better with MEG.
So what about the skull electrical credentials?
That's still there. That's biophysics. We can't. MEG doesn't have that problem,
right?
But MEG, yeah.
What were you talking?
No, go ahead.
No, talking about resolution and MEG does not have the volume conduction issues that EEG has, and that limits the resolution.
Yeah, that's I was thinking, but
yeah, but you can solve that problem. So intrinsically, does MEG see more than EEG see? And that's where there's room for discussion. I don't want to say that there's an absolute answer. MEG is not always better than EEG. People think if I have MEG, I have higher spatial resolution than I can ever get with EEG. Well, that would be true if you're not doing good EEG. It just means do your EEG better. It doesn't mean that the method itself is intrinsically limited. So if you can deal with connectivity issues, if you can get a high enough sampling scalp in terms of channels, if you can apply the right types of source reconstruction approaches, then you can get down to localization in a top order of percentage, which is comparable to what MEG is. The other advantage of EEG, I'm just trying to be provocative. The other advantage of EEG is, of course, you see both the radial and tangential sources, which is a major limitation of it. Right?
That is true, but the volume conduction issue is important.
Yes, but it's solvable, and you can model it. That's all I'm saying. It's important, and it shouldn't be ignored. But it's a tractable problem, and if you can, and I think we and others have addressed it, then the method itself is not limited in its spatial, well, it is limited in spatial, but not in terms of being a priori worse off than Meg. This is my only.
You could solve it with enough accuracy.
Yes, thank you.
Yeah. We actually spent a lot of time with human skulls and jelly molds to figure out what the distortion rates were, and most of the early calculations were all based on numbers that were 10 times higher than what we were seeing in terms of just putting a single electrode or even 20 electrodes inside the skull and electrifying with different depths. The distortion is small.
Okay. You had a.
Yeah, my only addition is, you know, there may be a debate about which is better when you just are comparing EEG and MEG. But then once you add in another neuroimaging method into that landscape, you find that MEG and EEG are right next to each other in this regard. So
Yeah.
it's sort of like.
It's one of those long held beliefs is, well, I'm gonna go and use Meg because its spatial resolution is great and EEG's is crappy. That's all I'm trying to dispel. You have another one.
Yeah, I was just curious, so you talked about kind of apples to apples is number of sensors versus number of sensors. In EEG systems, would you then extend the argument to if you could be infinitely dense, you would have infinite resolution? Does it
No.
keep going forever or?
Certainly not. But same thing with Meg.
Yeah.
Okay. Okay. This was really just meant to be kind of a preamble. The other is questions about signal to noise. People have argued that you can't look at single trial responses to the EEG. That's not true. But we'll come back to that towards the end. If we don't have time, I think, well, the man that took my slides ran off with the USB stick, but I'm happy to show you that as well, so you can have the references. Also, in terms of the analysis pathway, historically, again, this is my editorializing. I think the EEG community, much less so than the Meg community, had two camps in it. One that really came from experimental psychology and wanted a correlate of a psychological process, and another camp that came more from the physiology and physics, who wanted to solve some of the neurobiological questions and try and solve the inverse problem. And Meg historically has kind of been more in that pathway. And as a consequence, sometimes people get stuck because the lab has a history of doing things this way on a particular analysis pipeline. And that's led to some perception of EEG having a weak pipeline. And that doesn't have to be the case. But again, it's a historical opinion of mine that the types of students and postdocs that sometimes wind up using EEG are afraid to dive into methods. And hopefully we can dispel some of that. Usually people coming from Meg or MR don't have it. The other is the neurophysiologic understanding of what's generating the signals at the scalp. I think there people, unfortunately, especially in Europe, where many countries are banning monkey work, the students therefore aren't reading that literature and don't have somebody to teach them that literature, so they don't know how to understand what are the neurophysiologic underpinnings of the signals that we record in the scalp. Even though there's a large literature on that, in particular by Herb Vaughan and Charlie Schroeder. But I'm biased because I've worked with them. But there are others too. Those are just two that I particularly like. Okay, so another pop quiz. When was high density EEG introduced? And you can't answer, because you should know this. Any guesses on the decade? 50s, 60s, 70s, 80s, 90s? High density, so more than 64 times. 80s? That's good. And he did it with the thumb, which was also even more impressive because he spent time in Europe. So 80s? 80s? 90s? 90s. All right, the correct answer is 1972. So Derek Fender, this is from Caltech magazine, built, I think, the first, but maybe I'm wrong, but I believe that he was the first to really build a high density EEG system. It turns out that issue of Caltech magazine, my father was also. So I'm very pleased about that, because when I looked up this photograph, I found an article about my dad. Anyway, indeed, it was in the 70s. And what does that mean? We can really take EEG. This is a classic 80s advertisement from Neuroscan, or Electrocap rather. But the technology is becoming lighter weight and denser to allow us to do multi-person, simultaneous recordings, this hyperscanning, which I think is a terrible term, to also doing work in the NICU, to also doing field work and even client recordings, as well as brain-computer interfaces. These are just some examples. Okay, but how do we actually get to that? How do we get from recording EEG to doing high-density EEG to doing better signal processing? That's what I want to spend the bulk of our time doing and discussing. So imagine you're Hans Berger and you want to understand Gestalt psychology and this problem of perceptual completion. You design an experiment and you might record from a few channels. And to go from recording EEG to event-related potentials, you deliver stimuli. You then signal average. Right? You take these peristimulus periods of time, you put them together and average them, and you can then compare an average response to when there is a square to when there's not a square. I think that's all good for you. And you get some event-related potentials, but now you have to start thinking, well, how do I analyze these pre-processed signals to come to some neurophysiologic interpretability? And people started doing this by saying, well, I have this peak, that peak, etc. And Steve Hilliard, who I love to death, has created an alphabet soup of components. Every new finding he has a new name to it, and it gets very hard to keep track of. So I'm not going to give you all of those, but people like to put labels on peaks and call them a first positivity, first negativity, and so on and so forth. But that's not quite enough, because now we have high density EEG, and the norm is even doing high density EEG. And so your data set starts getting much, much more complex, perhaps. And having more data should give you more information and not more headaches, right? So if we have all of these brain squiggles or Pollock squiggles, and if you don't have the opportunity to go to MoMA, make an opportunity, absolutely wonderful there. Parenthetical statement. Right, so how do we confront these mountains of data? And these are some views from Switzerland so that you can appreciate where I get to hang out and do some work. Peter's already got to run all along that crest. So how do we confront mountains of data? Suppose we want to know the altitude of the mountains, right? And we're recording from high density EEG. The number of electrodes will impact the number of observation points we have, so we have a better cartographic map or geographic map of the mountain range. And what about global warming? How is that going to affect? And that's, if you will, the analogy for our choice of the reference. Well, the altitude that we put at any peak is going to change as sea level rises, right? So altitude is going to be reference dependent. Our ability to detect changes in amplitude will be dependent on the numbers of channels that we have at our disposition. And what about the shape of the mountains? So the shape of this mountain range will also depend on having enough sample in space, right? If you want a good map, you need to sample every meter, every yard, every foot. Global warming has no impact on the shape of the mountains, right? Well, sorry, erosion and things. Let's imagine there's no erosion. If that's where you were going with your. Imagining that there's no erosion, just the change in where I call sea level. There's actually an organization on the planet that decides where it is sea level, and they debate where sea level is. Sea is not flat. Again, parenthetical issue. The point is, topography is reference free. Right? Now, why do I keep talking about the reference? Why is this so important? Well, do we think or not this would change my results? Yes, no, I use that. I had other less PC things in here, but people pointed out to me that I can't do that, particularly in federal buildings. So there is another version of this, but I've turned into your instructions.
And to clarify what results mean.
I'm sorry?
Results, wait, we interest my results.
Okay, statistical outcome. I don't know. What I get in my data. Call results whatever you want. Yes, no, yes, it absolutely will. So let's do a thought experiment for those that speak German, like a Gedanken experiment. Who is telling the truth, right? And if you go out and read a bunch of different EEG books, you'll get a bunch of different opinions. They'll tell you where to put the reference, what the reference does, what the electric fields actually do. And if you're a student entering into the field of doing EEG, you're lost. Who's telling you what to do? Well, usually your PI. And your PI is doing it because their PI did it, and so on and so on. But if you're in the clinics, you need to know the truth about what your data is telling. In particular, in the clinics. Obviously, anywhere you want the truth from your data, but especially in the clinics. We'll come to that. So Steve Locke, in his Bible about EEG, came up with a proposition that he calls the no Switzerland principle. Now, that's fine. And the reason he calls it that is because there's no electrically neutral site on the header block. He's not actually picking on the country. Even Swiss neutrality was not their choice. It was imposed by Napoleon, but we can talk about that another time. The point of his principle is that there's no neutral site, and yet, because you're measuring voltage, which is by definition a change between 2 points, you need a reference. Okay? And so you need that, but what he doesn't talk about anywhere in his book are the consequences. How do you choose? What does that do to your data and therefore your results? So let's take this a bit farther. Let's imagine we're looking at Peninsula illusions and we choose a vertex reference. We observe a statistically significant effect by whatever criterion between 250 and 400 milliseconds. We then look at the topographies of this and we look at where on the scalp we see statistically significant differences. Okay, these are all posterior electrodes. Sorry, front is up, left is left, right is right. Okay. And then along comes Pete and he says, you're using the wrong reference. In my lab, we use master reference. And when I do that, I get no difference at that electrode. I then look at the topography again, and I see all of the effects statistically are now on frontal electrodes. So if you're an experimental psychologist, you'll then interpret your data very differently depending on which reference you use. Is it illusory contours something that's happening in visual cortices or in frontal cortices? Now, I've deliberately taken an extreme case, obviously, but you get the point. The choice of the reference changes your results. Now, how does it change your results? Some people will say the choice of the reference just redistributes them in space. It's the same statistical, you have a question there? You're just thinking. It just redistributes where they are in space, but the statistical outcome is the same. Any thoughts on this? All right, let's think about it. It actually changes the noise and the error, and therefore it changes even if there is a statistical result. So this again is just an illustration. Here I have the same data analyzed either using a nose reference, not noise, or a common average reference. And what you're seeing on this panel here are the number of electrodes that meet a certain criteria. Again, statistical criteria are arbitrary, but imagining that we use the same one, you can see that over time, the number of channels that are showing a statistically significant effect changes, right? And you can see that in the average standard error across sites as well. So you're not just moving them in space, you're changing whether or not there is an effect. That's a problem. That's a big ass problem. Can I say that? So now you can go back and you say, wait a minute, I just spent, I don't know how much money, 60,000 buying a 120 channel system. I've just made my life so much more difficult. Why don't I just go back, buy a Muse and record from 3 channels? Is there actually any added value in having high density EEG? Yes. And I'm going to argue why that's true. Okay. So if we come back to poor Ben Stiller and Robert De Niro, we need to know which results are true. And to do that, and to do so if we have to worry about patient lives or even doing good research, we need high density EEG. But you should take into account peer pressure. Like any good student, you shouldn't believe anything simply because I'm an old fart doing this for a long time. Right? You should also try and get rid of my influence or your own influence on what you're doing with your data. Try. You'll never eliminate it. And hopefully it's replicable and should give truth. Right? Hopefully. So how do we get to that? How do we then get added value out of high density EEG? Well, Steve Block will tell you, record from 62 to 32 channels, analyze single values after cleaning it up, report interactions between electrode and scope location, but that's about it. He actually says that. If you read not what's in the book, but the online supplements of his book, he tells people how he wrote, and I don't know if you talking about high density EEG, but he has no intention of actually performing high density EEG, which is such a wrong message, I think, to you. I adore Steve Light. I think he's absolutely smart on many, many things except this. At least this. On the other hand, there are others who advocate recording from at least 64 channels. Analyze the data in a reference independent way that gives you neurophysiologic information. And absolutely report these changes that you're observing in terms of topography and strength. And I'm going to show you how to do that. So this leads to the Iowa principle. Now, for those that know Steve Block, they might know that he worked for a long time at the University of Iowa. I have nothing against the state of Iowa, absolutely lovely, beautiful part of the world. But it leads to the following. ERP voltage waveforms depend on the reference. I think they actually offer very limited neurophysiologic interpretability in and of themselves, and therefore can get you in the middle of nowhere, which some people say is fine. But again, it's not meant to be anything about the Midwest at all, quite the contrary. But I'm playing on no switch limit. So can we surmount this? Can we get around these limitations I just told you about in terms of voltage waveforms? Yes, no, don't really care. Obviously, yes, otherwise. Right. So what do we really want to know when we do EEG or even MEG? But here I'm talking about EEG. What we want to know, is my experiment leading to a change in strength or amplitude, a change in the network that's active in the brain, a change in the latency of whatever's active in the brain? And can I differentiate these three things from each other? And can I do this on an individual basis? Okay. Well, how do we get there? Well, this is what you get from moving to America, to Switzerland. This is an actual view, this is not fake. This is the Dent du Midi, which is right by where you were. This is in fact what you see out from Champéry. Wonderful hiking there. This is the Chateau Chillon. Any English poet fans? Byron, the prisoner of Chillon. He spent one night there. He wasn't exactly a prisoner, and he etched his name in the wall. It was the same summer that Mary Shelley wrote Frankenstein. Way more interesting person to read than Byron. Awesome book. One of my favorites, Frankenstein. She was 18 when she wrote it. Right. So what do we gain from moving to Switzerland? Well, we gain what I would call the Swiss Alps principle. What that tells us is, again, the topography of the electric field of the scalp, the shape of the mountains, is referenced in that. Now that's a big deal. And it's a big deal because we know from von Helmholtz and others that a change in the topography means a change in the generators that are active inside the brain. So, yeah. Are you just agreeing?
No, I was going to ask a question. So you're kind of showing these topographies, but you previously mentioned that your references noise has a lot to do with how you measure things. Wouldn't that influence?
It doesn't change the topography. It changes the noise across whatever you're averaging. But the instantaneous topography, no.
So not even if, okay, so if it's isolated to certain electrodes that would use that as a reference, wouldn't like some mountains be higher than the other than if they had different noise correlation?
So if you have, say, like both mastoids, you could end up, so electricity goes to basically half of least resistance. So if you do both mastoids and they have slightly different impedances, you will.
You have an undefined reference.
Yeah, you'll have it sense.
So yeah, Nunez and Shrinivasan talk a lot about this. Right. So I think we need to separate out two aspects of the data processing pipeline. One is getting clean data. I'm assuming that people can acquire clean data. Then the question is, what do you do once you have the data to have clean analyses, clean, interpretable.
Yeah, I guess I was making the assumption that if something changes, and let's say your reference becomes more noisy, that tells us something about the noise in the rest of the
Yes.
system as well.
For sure.
But that doesn't have to be true.
Doesn't have to be true at all. That's, yeah, garbage in, garbage out principles. But I'm assuming, I'm tabling that part. I'm assuming people can get clean data. Then it's all what do you do once you have. But you're right.
We have big data.
Thanks, Steve.
Okay, so if we start from the observation that topography is independent of the reference, and if we start from the other observation from biophysics regarding changes in topography being neurophysiologically interpretable, then we want ideally a way to see those changes because it doesn't depend on my choice of the reference and it gives me interpretability. And then I don't have any ambiguity. It's not me intervening to say, this is what I think this waveform change means, right? So how do we actually do that? How do we compare Switzerland to Iowa mathematically? And one measure to do that is called global field power, which is simply spatial standard deviation. Now, this audience, I don't have to worry about showing equations, but if you stand in front of experimental psychologists in general, they don't like having anything beyond standard deviation mathematics. I'm drawing vast generalizations, but the math averse in general. I say that because I am. Right? Now, what that tells you, by the way, that's just the formula for standard deviation case. Don't know what it is. But what that will tell you is, sorry, I went too fast. There are more mountains and hills in Switzerland, more variation in space than in Iowa, which is flat. It just tells you if there's variability in your electrode montage. What it doesn't tell you is where that variability is. Right? If I take the IQ of everybody in this room, it doesn't matter where you're seated. The standard deviation of us will be the same, or height, whatever measure. Clear? So how do we know when we have a change in the mountains? Well, GFP can't tell you that, or global field power. But global dissimilarity can. And the global dissimilarity is simply the root mean squared difference of two normalized vectors. They're normalized by their strength. It's directly related, by the way, to Pearson's correlation coefficient. So if it's easier for you to think in terms of correlation, think of it as that. Dissimilarity is really just the distance between two electrons. Euclideans. Sorry, talking about these kinds of things. Okay, I'm going to show you the maths of how it's really done, but this is the general. So two very, very simple formulae give two very different kinds of information about the electric field and scalp, both of which are referenced in the paper. But now I have two different measures of two things I want. So we're already off to a good start. But how do we actually do this? Let's suppose I had a 16-channel montage, which I wouldn't advocate, but for teaching purposes, makes life a lot simpler. Warmer color is positive, cooler color is negative. I then take a second condition and I just multiply every value by 4. And a third condition where I take the inverse. And a fourth condition where I kind of shuffle things a little bit, not too much. All good? Too fast, too slow? Perfect. Now, how do I calculate the global field power? Well, I literally take the squared value, sum them up, divided by the number of channels to take the square root. Right? Again, the maths are really, really not hard. I won't say trivial because that's not fair to people, but they're not hard. Right? So you can see that even though those two conditions are inverted, the global field power is the same. All good. Right? And same thing for conditions 2 and 4. Those are 4 times because that's what I did today. But what that shows you is that the global field power really is sensitive to strength. But it's not sensitive to anything spatial whatsoever. All good. All right, so now what I can do is normalize my data by that global field power. So I'm going to divide each and every value of the 16 by the instantaneous globe. When I do that, I can now start comparing apples to apples, as we said, in terms of the spatial distribution. So I can, yeah.
So that's equivalent to turning an angle direction.
Yeah, exactly. I wasn't sure what terminology to use, but yes, exactly equivalent. So you can see that conditions 1 and 2 really do have identical topographies, even though again the strength was initially higher for conditions. And the spatial correlation would be 1. 1 and 3, of course, it's inverted. So dissimilarity goes from 0 to 2, spatial correlation from 1 to -1 in terms of scaling. And if I then go to condition 4, I actually have dissimilarity of about 0.43 and a spatial correlation of about 0.9. So you can actually have things that appear highly correlated, that all the same have subtle and maybe detectable differences in terms of their topography. And they might be detectable if you have enough channels. All good? And it's only about space. You've gotten rid of strength. So now you have 2 orthogonal measures about strength and topography. Okay. The statistics on this, sure, the global field power you can treat like any time series. So I'm not going to dive too deeply into what you can do statistically, but that's up to you. Dissimilarity, you can more often than not, what we advocate is using non-parametric statistics, and you can use randomization approach, you can use permutation approach, whatever you like. That just gives you, of course, a data-driven distribution of values. If you put a p-value on it, problem is, you know that the topography is different, but you don't know how and why. Right? So you're going incrementally. It could be that a given period of statistical significantly different topographies is because one condition has one map, which we'll call A, another condition has a different map, which we'll call B. It could be that. It could be one condition has A and B, another condition has B then A. It could be any, you can amuse yourself with any number of combinations. But you could already stop here. Could, I'm not advocating. You cannot stop here and say, I know when I have a change in strength, and I know when I have a change in topography, and it's driven by my data, and I didn't have to do anything to it. I didn't interfere with my data, which is, I find nice. And I can take my data in an analysis pipeline and compare it to another data acquired here and compare it. Also nice. Sorry. So, this is a trick question. Latency and polarity define an ERP component. Now, the quote here is from Justice Potter Stewart about obscenity and pornography. But I wasn't sure if I could put it. It's like porn. I know it when I see it because I didn't want you to think that I was saying something wrong. But some people think I know what's going on in my data when I see it. Maybe. What defines a component in the EEG? It's certainly the latency, but it's not the polarity, because the polarity at a waveform can change. It's the topography and the latency. Okay. Interestingly, if you take a movie of either EEG or MEG, I'm presuming you're an MEG guy. You go. I do go. Oh, God. All the more reason to like it. If you actually look at a time series of topography, what you hopefully observed just looking at these data, and I deliberately didn't make a movie, but frame by frame, is that you and your eye will start clustering into, well, it's first one, I'll do it again. First one topography, and then different topography, and then different topography, and different topography. And what we find is that the temporal structure of EEG and MEG is not random. There is structure to it. And can we identify it? Can we actually, oops, animation didn't work there. Can we actually take a whole time series and reduce it or compress it into a set of template topographies? And that's all the topographic clustering is seeking to do. And if we can identify that alphabet soup, then we know why we have a topographic difference to begin with. And that gives you these building blocks, or some people have called them microstates. I'm not a big fan of that because it gets overinterpreted, which is also the 50-year anniversary of Dietrich Lehmann describing that this year. But that gives you these processing steps or components. Now, there are ways to do clustering. I didn't realize that Jane Lynch took over The Weakest Link in the United States. She's an awesome actress, way better in these independent movies. If you haven't seen them, very, very worthwhile to watch these two films. Very snarky and well, and they're generally speaking for EEG and MEG, two families of clustering approaches. One based on k-means clustering, the other based more on a hierarchical approach. Are clustering approaches familiar to people? So all of you, is there anyone in the room who's unfamiliar? And it's okay, because then it gives me a purpose for being here. Awesome. So k-means is much more of a top-down approach. You're saying a priori how many clusters you think there are, and you're trying to force fit the data into those number of clusters. Hierarchical, you're much more of a bottom-up approach or weakest link approach, where I take everybody in the room and I figure out who explains the least amount of variance, which would probably be me, because I have no hair and you all do. So you get rid of me and you'd replace my head with Peter's or Pete, whoever you like, right? Is that generally clear? I can walk you through k-means if you like, or I cannot. So k-means, I'm going to put my data set in one bucket. I'm going to strip off condition, time, all the meaningful information. It's just a big bucket of data. I'm going to extract from it n number of template maps. And I'm going to calculate the spatial correlation that I showed you before, or dissimilarity, between each of these three maps, in this case, and my data. And there'll be periods with the red wings, green wings, blue wings. And collectively, those three maps will explain a certain amount of the variance in the collective data set. But maybe they're not as good as they could be. So I'm going to then average all the points where the red was higher than everybody else, the blue was higher than everybody else, the green was higher. Now I'm going to make a better red, a better blue, and a better green. And I'm going to repeat that same process, spatial correlation. And that is going to give me as good as those three template maps will explain the whole collective data set, right? And now I'm going to repeat that for a different set of three. And I'm going to take the three that give the highest spatial global explained variance. That's as good as three will do. And if I do enough randomizations, it's okay. Because by chance, I could get neighbors, or by chance, I could get data that are far apart from each other. Then I repeat this, repeat this 4, 5, 6. All right. So the challenge that we have are two. One is how many maps best account for the data, and the other is what's the specific pattern in the actual data in terms of condition group, etc. Now that second problem is not a problem at all, because you just re-put the labels back on your data. You took them off, but you can put them back on. The first problem is more complicated. And there are many, many criteria one can imagine using. One that we've historically used, and is anyone who speaks Polish? I cannot pronounce this name for the life of me, so I just call it KL. But I think it's something like Shronovsky, but there's a lot of movement of my mouth I can't do. Anyway, what it seeks to do is have two clusters that are far apart, and the members of those clusters as close to the center of mass as possible. But there are other criteria that can be used as well. Reshe and all the neuroimage do a nice job describing many, many different criteria. I think I did put it. Yeah, there are other criteria that can be used. In my experience, you can use these different criteria, but if you do your clustering properly and if your data are clean, it doesn't change much in practice. What you get at the end, though, is a pattern of topography in time. Let's suppose you only had two conditions, the illusory contour and control. It could be two different groups. It gives a hypothesis at the group average level, in this case, because I put in the data I put into the clustering with the group average. It gives a hypothesis of this is what I think is happening. I think this is what the clustering thinks is happening. So one condition has a yellow map, the other condition has an orange map. One condition doesn't have any red, the other has a red. This happened to be, by the way, for face processing. That's where these data come from, which shows that the M1 modulation to faces is actually not just gain, but it's actually change in topography. What you can then do is ask at the single subject level, is that actually the case? And you can do backfitting to test, is one map better characterizing one condition or one group or one whatever you want, and another map a different condition. Now this is a perfect interaction. It can be many different variations of this. And it can be other dependent measures. It doesn't have to be the frequency of the map presence. It can also be features like best correlation, the global explained variance, the first onset, first offset, where you can really get the dynamics of these maps over time. And again, it can be MEG or EEG. I'm talking about EEG today, but the pipeline is equally applicable to any time series actually, where you have topography. Good. So I already hinted at this at the beginning. Do we need to actually do signal averaging to get an event-related potential? No, not at all. We can take that same approach to clustering. Here, what we introduced, but it's not, again, not the only way to do this, was using a mixture of Gaussians to model the data. So for every single trial, you can identify the posterior probability of the data belonging to any one of different Gaussians. And you can label that trial according to the one with which it best fits, or best matches. And what you can see here, right, are different trials and different maps, and you can hopefully see vertical colors of vertical bands of colors. And you can do this not only for one condition and one individual, but you can do this across individuals, across conditions, and explode your data set and actually see how much noise, are there noisy trials. So it's a good way to also clean up your data, but in a data-driven way. So you're not making assumptions about, like ICA does, about orthogonality of the different components. You're not making assumptions about spatial distribution of those. You can do that and then do things like drive brain-computer interfaces. You can also do this to do single patient analyses, which we've done in coma, which I'll come to. So I can stop there. I can give some clinical examples because I wasn't sure who would be in the audience, and I knew from Tuesday there were some people working in the clinics very actively. Or I can stop and we can talk.
So I'm kind of curious how the clustering relates to, how does it optimally track brain-computer interfaces as opposed to?
Yeah, so oftentimes brain-computer interfaces will try and look for a feature in a channel, or sometimes a cluster channel. So looking for, I don't know, P300. So you're looking for an amplitude change. Now that's a feature. A different feature could be a unique topography that characterizes P300. And is there more signal to noise in time or in space? And I would argue both, but certainly in space compared to an instant. And that's the added value. What it can also help do is deal with variability across patients, or even within a patient across data. So in this case, a person receiving focal electrical stimulation for control of movement, when are you training the classifier? Are you doing it on a daily basis? Are you doing it each time you put the cap on? Are you doing it over time? And again, the spatial configuration can be less sensitive to those changes. This is the short answer. Does that answer your question? Yeah.
I have a question about the signal trial or EEG analysis. I've typically seen this in the context of very robust events.
Yeah.
You know, the visual stimulus is very obvious or engaging in some sort of imagery in a prolonged way. Have you seen this implemented with brief, subliminal, or near threshold?
Yeah, so we did it with, we published it even with NeuroImage. I want to say yes. We did this with semantic categorization of environmental sounds that were too short to explicitly categorize. And that worked really well.
What was the duration?
The duration of the stimulus was, I think, 200 milliseconds. Those were sounds.
Sure.
We've also done it with in a forearm bandit paradigm in terms of exploit and explore behavior. And so there, the stimuli were long but subtle in terms of changes, and behavior was also very simple. And that, again, worked quite well. People have done it with, visual quadrants. Their classification problem is very challenging, I would argue. But it was more to demonstrate that we know that the input should give different topographies. Do we see that on single trial? I mean, despite changes in cortical gyrification across the subject. So that was the motivation. Did that answer?
Yeah.
Okay, so I'll give 3 very quick examples in the clinic. So Dan Fine has worked on psychiatric populations, and one of the things that we tried to work on was identifying what's actually going on in schizophrenia. It turns out that not only is it a thought disorder problem or psychosis, there's also a sensory dysfunction that is a hallmark. And it's not just a change in the gain, again, in this population, but a change in a different meaning of gain. Sorry. But we also could do this using add-on treatment of N-acetylcysteine, which is a glutathione precursor. And this was in the mismatch negativity paradigm, where we could see changes in the event-related potential and changes in the topography and source reconstructions as a function of add-on treatment that preceded the clinical metrics that were visible by at least 6 months. So EEG is very powerful in terms of detecting these kinds of things, but I think I'm preaching to the choir in that regard. Another fun one was looking at kids with cerebral palsy. I put this in because Diane and Tom, who were there on Tuesday, room, maybe they're in the Zoom room. There you have a child that has a more affected and less affected limb. This is upper limb cerebral palsy. We then typically treat them with constraint-induced motor therapy for 5 days, as well as occupational and fine motor therapy. We then want to look post-training if there are positive effects on the affected limb and negative effects on the unaffected limb, which has been put in a cast for a week. And what we find is, in fact, the post-treatment somatosensory response to the unaffected limb makes it look more affected. And the post-effect on the affected limb, of course, looks like the unaffected limb beforehand, in terms of the topography of the electrode. So you have a double-edged sword. On the one hand, you're improving what's bad, but you're making worse what was good. And we can do this on an individual case. Another domain I think I heard talk about on Tuesday was cochlear implants, and seeing in individual patients whether they're using more visual approach or an auditory approach to understand speech. And of course, cochlear implanted individuals are not compatible with MR or MEG. So developing EEG tools for that is obviously a good thing. So to come full circle, hopefully you learned about all these different things. Hopefully you see that the choice of the reference has a dramatic effect on what you're doing with the data. There is an absolute added value of doing high density EEG. We can indeed measure global field power, global dissimilarity in a very mathematically straightforward way that are independent of me or the observer. And I think this gives a good pipeline for reference independent, data-driven, and I think interpretable analysis. It's not the only way. I'm not suggesting that people that do things differently are wrong, but they should just be aware of what they're doing, and also I should be aware of the caveats of what I'm doing. So I'll happily take more questions if you have.